Hello everyone, and now we're in example 10-3. Oh, there he goes. 10-3. Now I'm going to read the problem statement and then we'll jump into this problem. So, let's see what we're given. It says an ASTM A36 steel rod, which is 6 meters long, must be capable of supporting a tensile load of 11 kilonewtons. Okay, without elongating more than 7 millimeters. Or exceeding an allowable tensile stress of 150 megapascals. Calculate the required rod diameter to 1 millimeter. Okay, so find D, but in increments of 1 millimeter. So remember, if we're doing increments, if we're in between two, we gotta go bigger because we can't go smaller, otherwise it fails. Okay, now it gives us two conditions here. We're gonna hit one of those first. We're probably not gonna hit them at the same time, so one of these is gonna matter more than the other one. So what's probably the best idea is to calculate what the area of our rod needs to be and see which of these gives me a bigger value. So whichever one gives me a bigger value, that's the one I've got to go with because otherwise it will fail. So let's calculate this out. So just based on the stress, what I have is 150 megapascals is equal to the load over the area. And sorry, I should have written this beforehand. Stress is equal to the load over the area. There we go. And if I plug that in, what I get is I have 11,000 over A. If you're wondering why did I not convert megapascals to regular pascals, because of that nice little trick, which is that 1 megapascal is equal to, oh my, 1 Newton over 1 millimeter squared. Pen's getting on me a little bit there. Let's see, there we go. And so with this, I can get the area in millimeters squared without having to worry about converting anything. That's always nicer. So if I do this, I bring everything around. And what I'm left with is that it is 73.3 millimeters squared is the required area just based on this particular condition. Anything less than this and my object will fail. Now let's try the elongation. Now with elongation, it's different. I'm not going to use the stress equation because I am given a specific elongation, not strain. I'm going to use my delta equals PL over AE equation. The Plee equation, the Flee equation, depending on who you talk to. Now, the E is one thing we don't necessarily know just off the top of the back, but it told us that it was an ASTM A36 steel. And we can check the appendices to figure out that the modular elasticity for this is going to be equal to 207 times 10 to the third megapascals, which is also 207 gigapascals. So this will be helpful. Okay, and then with that, let's keep on plugging everything else in. So first off, we need to solve for area. So I do that, and I'm left with is PL over delta E. I'm going to use that same helpful trick that 1 megapascal is equal to 1 Newton per millimeter squared to allow me to skip through a lot of the conversions I would normally need. So all I'm going to do is convert my kilonewtons to newtons. So what I'm left with is 11,000 newtons times 6,000 millimeters all over 7 millimeters times 207 times 10 to the third megapascals. And what that comes out to be is 45.5 millimeters squared. So this guy is bigger. And therefore that means the stress is most important. So if we have to use one, we're going to use this guy to calculate the diameter. Okay, now we used In the previous example we did, that was example 10-2, we did the area equation, which is simply pi over 4 times diameter squared. You can find this in the front of your textbook. And so I'm given an area. So that area is 73.3 millimeters squared. That'll be equal to pi over 4 times diameter squared. And I just solve. And what I'll get is that the diameter is going to be equal to 73.3 times pi over 4 to the square root. And that will come out to roughly 9.66. That's a terrible 9. There we go. 9.66 millimeters. And remember that we asked for millimeter increments, and so we always have to go up. Always go up. So instead of 9.66, we're going to have 10 millimeters. That would be the correct answer because it comes in 1 millimeter increments. You need to make sure that you have enough. If you go lower, it will fail. So enter 10 millimeter rod. Okay, that's the end of example 10-3. And I will see you in the next example very soon. Have a good day.